So the first important example for the induced cup product which we are going to discuss is the two-hold torus. So we will denote this by M, and it is important that we first draw the torus and understand it. Okay, so now I am going to draw the torus. Okay, so we have to take orientations of the edges into account because that will be important in the computation of the cup product. We will also have to triangulate this torus, and that will be important in determining the co-cycle maps. So what will happen is, basically, once we triangulate it, we will have a lot more edges, which you will see in a minute, and the co-cycle condition would essentially mean that if you cut these edges, you have a 1, and if you do not cut these edges at other places, you have 0. So this will become more clear as we proceed in the lecture. So this is the center point. I have not drawn arrows in the central part, but it is clear the arrows all are to be drawn going from center to outwards. Yeah, so from the central point to outwards we have arrows going. So each of these two simplices has an orientation. Okay, and for example, orientation given by a single edge A1, there are two edges A1 and A1. So one of the edges will give you clockwise orientation and other will give you anti-clock. So this is the cup product we want to talk about. We take cohomology 1, and we want to land in the cohomology 2 of M, where M represents the two-hold torus. So this thing is given on page 207 of Hatcher, in case you want to read that part. So first of all, notice that this is isomorphic to the dual of homology group. Why is it so? Now this follows directly from the universal coefficient theorem. You know the homology groups of a two-hold torus are consisting of integers, and which will make sure that the X group will be 0 because it is acting on a free group. So let us write what I have just said. Now you can also compute cohomology groups by writing down the chain complex of the homology associated, and then write down the co-chain complex by applying the home, and then compute the cohomology groups. Okay, now back to the question. Now this isomorphism above shows that the basis for the cohomology group H1 is determined by the basis of the homology group. So let us write this down. Basis of homology group determines cohomology group basis from the isomorphism above. So we know basis of H1, the homology group are A1, A2 and B1, B2. So this will cohomology classes I'm going to write as alpha I. Now the cohomology classes are just not enough. We have to represent it by a co-cycle. So what the co-cycle will do, as I mentioned before, the co-cycle, say alpha I, is represented by phi I. Now this phi I will take value 1 wherever any edge cuts alpha I and 0 to other edges. Similarly, for basis bi we assign beta I, and I should be writing alpha I and bi in the Instead of AI and BI, I should be writing alpha I and BI. So again, corresponding to beta I have phi I or xi I, which assigns 1 to every edge which cuts beta. So let us write down what is alpha I. Now alpha I is corresponding to edges AI, so it is joining A1 and A1. So for example, alpha 1 joins A1 and A1, and beta 1 joins B1 and B1 because it corresponds to basis B1. Okay, so this is, which I have just drawn, is beta I, and alpha I had drawn previously. Now I want to talk about phi I and xi I. So alpha I has to be represented by a cocycle, and as I mentioned before, phi I essentially counts the number of times alpha I cuts other edges. So phi I is a cocycle. I'm just writing the cocycle condition, and phi I counts how many times it cuts alpha I. So I have said before that it assigns 1 to alpha I and 0 to other edges. So let us first write down what does phi I do. It assigns 1 here, 1 here, alpha I is cutting edge, alpha I is again cutting an edge, 1 here, alpha I is again cutting an edge, 1 here. What about, so similarly we will talk about xi I, which represents beta I. So for example, xi 1, 1 where beta 1 cuts the edges. So I'm writing 1 where beta 1 cuts the edges. So phi I counts intersection of alpha I with arcs, and similarly xi I counts intersection of beta I with arcs. So first thing is I want to write what is phi I coupled with xi I. Yeah, so essentially phi 1 and xi 1 we will take. So you know in 2 torus there is only one vertex, but I'm going to write these multiple vertex so as to know which simplex we are operating in. So the orientation here is in the direction of A1, and yeah, so we will talk about that vertex, that simplex. So it acts on K, V0, V1. So obviously phi I cup xi I has to act on all the 8 simplices, but I'm starting with just one of them. So standard formula. So notice that the orientation was important. We have K, V0, V1. So that is the precise direction we are going in. So on K, V0, obviously alpha I does not intersect it, so it takes value 0 here. What about xi I, V0, V1? Now on V0, V1, only alpha 1 intersects it, but not beta 1, and xi I counts intersection of beta 1 with arc, so it's pretty clear it is 0. Then we do phi I cup with phi I cup with xi I, the second simplex. So again we have taken orientation into account. Orientation is determined by the edge BI or B1 in this case. So let me write this down. Again, the orientation is given by edge B1. So what will this be? Now KV1 phi 1 counts how many times alpha 1 cuts it. So obviously alpha 1 cuts KVI or KV1, so you get 1 there. And what about the second edge? Obviously V1, V2, as you can see, V1, V2 is cut by beta 1 and you get 1. You will see this is the only non-zero part here. So we have already seen the cup product phi I cupped with psi I, where phi I represented alpha I and psi I represented beta I, and in particular we computed phi 1 cupped with psi 1. Now you can do that for all the 8 simplices. Yeah, but there is only one non-zero value which we already computed. So that is kind of easy to see for phi 1 cupped with psi 1, because to have it non-zero, both alpha 1 and beta 1 should occur together in the same 2 simplex. So now I want to talk about H2 part of it. Now you know that in this homology group 2, the entire 2 cell generates the second homology group, and this say entire 2 cell is C. Now here in this case, since we have subdivided the 2 cell into 8 different parts, so these entire 8 simplices form 1,2 chain. So this part C is what generates the homology group. So we can add some more reasoning to it, that since there are no 3 simplices, C is not a boundary, and therefore it generates the required homology group. But it is very clear from the way we compute homology or cellular homology. So we want to find the corresponding part for cohomology. Now obviously we have taken the cup product of phi I cupped with psi I, and it has to land in H2, and we have no other option but to say phi I cupped with psi I, what it generates in cohomology is equivalent to what C generates in homology. So say C generates the second homology group. So this we have already seen. So this will be 1 only on that particular simplex. Yeah, because alpha 1 and beta 1 both have to intersect, and they intersect only there. So let us denote this by gamma, phi 1 cup psi 1. So C generates the homology group, and the corresponding generator for cohomology group is this. So let us draw it down what we have done till now. So this was A1, B1, A1 again with the opposite orientation, B1 again with the opposite orientation. This was alpha 1 which connected to A1s. This is beta 1. These are the vertices. So now in particular I want to talk about the cup product of psi 1 cupped with phi 1. That is precisely the opposite of what we have written above. Yeah, so this is what we want to compute. What is this? So this we will obviously you have to compute it on all 8 simplices, but I'm going to write down the value in the only place where it will get a non-zero value. That will be on this 2 simplex represented by KV3V2. Now notice that I'm writing KV3V2. It is opposite of the orientation which we took on the previous slide. So we have to put a minus sign now. We have no option, yeah. So you put a minus sign. If phi1 is acting on KV3, so as you know, xi1 which acts on KV3 is 1 because it measures beta 1 intersects KV3, yeah. So that is it. So second one is just alpha 1 intersecting V3 V2. As you can see, get 1 there, carry over the minus sign, you get minus 1. So as you can see that there is no commutativity, yeah, so the sign is changed. Now let us write down what we have. First notice that alpha I coupled with alpha j is 0, yeah. Both alpha 1 and alpha 2 do not meet. We will draw this. Similarly, beta 1 and beta 2 do not meet. Since they do not meet, so on a single simplex you cannot have both of them, and therefore one of them is 0. So therefore when you take the cup product, it will be 0. So let us draw it. So this was A1, this is A2, and this is A2 again. So this is alpha 2. Now you see alpha 2 does not meet alpha 1 which we have drawn before. So therefore alpha 1 coupled with alpha 2 or alpha 2 coupled with alpha 1 is 0. Yeah, you have to compute it on each of the 8 simplices. You have to represent alpha 1 with phi 1 we have already representing, then you have to represent alpha 2 by phi 2 and then go on. Or you can simply say they do not meet and therefore it is 0. Similarly for beta. So now we need to write this down more precisely and clearly. So yeah, so first thing is again, so this is 0 whether I is equal to j or, yeah. Yeah, so it will be instructive to just see if you cup phi 1 with phi 1 what will happen. It will again give you 0 because one of them has to be 0. Yeah, so this is important that you check I equals to j. And the second part we have checked just now by showing 1 and minus 1. So the generator is gamma which represents 1. You see that the sign reverses itself. So now I'm going between co-cycles and the classes. That is understandable and important to keep in mind that when we switch from classes to co-cycles, there's nothing much, it's actually absolutely nothing lost in it, but just to keep it in mind. And that is it. That is the structure we get on the cohomology classes. This structure computation is important to compute the graded ring.